Welcome to lecture 34, where we're going to be talking about circular orbits. So we're going to just remind ourselves how circular motion is essentially possible. What does it take? We'll describe gravity as the centripetal force, right? That's kind of the key idea, and everything else follows from that. Everything else becomes easy once you understand this. We're going to look at two examples. Phobos, which is one of the moons of Mars, and then geostationary satellites around the Earth, and I'll explain what those are. Let's have a look then. Here I drew some different types of orbits that you might find. You might have circular orbits, where something's going in a circle. With the sun in the middle, the Earth is going around it. If you want to be pedantic about it, there are no circular orbits anywhere. There could be in theory, right? But in practice, you're always going to have elliptical orbits. But a lot of orbits that are elliptical in, say, in the solar system, let's stick with that, they're very, 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 very close to circular. Like all the inner planets, from, Mercury, pretty much, the actual inner planets, Mercury, Venus, Earth, Mars, but then also Jupiter, Saturn, Uranus, Neptune, they're all fairly circular. If you go further out, we tend to get quite a few elliptical ones. So, for example, Pluto has a pretty elliptical orbit. Eris, all those just smaller stuff out there, those dwarf planets and planetoids in the outer regions of the solar system, they all have very elliptical orbits. And then comets, right, that go around the sun and then they're not seen for hundreds of years before they come back, hundreds of Earth years, while they have very elliptical orbits. We are not going to talk about those in this course, not because we can't. They're well understood. We just have to do a little bit of math of ellipses first, and notions such as the eccentricity of an ellipse. And there's no inherent reason why we can't include this. We couldn't be able to include this in this course, but because there's only so much time, we won't be able to talk about elliptical orbits in any detail. There's also this type of, let's call it a trajectory, not really an orbit, where something is simply going too fast. Here it comes, it gets attracted to the planet right here, or the sun. It makes it change its direction, but it's just too fast, it zooms off into the distance, it's never seen again. This is the hyperbolic, it's a hyperbolic trajectory. And again, if you understand these ones, we can also talk about these ones, except we're only going to focus on these ones here. Maybe we'll get time in class to talk about those, or you can look them up yourself. Although you might have to change to a slightly more advanced textbook than the one you're using with this course. If you decide to become a physics major, which you definitely should, then you'll definitely meet those once again in a more advanced mechanics course. In any case, let's focus on this one here. Right, and as I said, this is a very good approximation to all the inner planets, to the Earth's moon, to a lot of satellites. So circular orbits are extremely important. Let's remind ourselves how they work. So here's my planet. As circular as it's going to be. Here's the planet. So somewhere above here, there's my satellite. Could be a man-made satellite, could be a moon, doesn't matter. Right? And if this thing just sits there, right, let's put it there in space, well, it's gonna fall down, crash into the planet, and that's that. Giant explosion, but there's no orbit. If I want this thing to go in orbit, it has to start off going sideways. Maybe this was some rock that came by, it got knocked around a bit, and it ended up in this spot, going in this direction with a certain velocity. Could be a spacecraft somebody shot, it took off, it went up here, and it, you turn on your thrusters in just the right way, that you end up, when you're here, going in this direction with a certain velocity. So what's going to happen now? Well, there's going to be a gravitational attraction to the Earth, right? So this pulls you down. Mark those in red. Where's your velocity? Let me mark it in green. Is this way. So you're flying sideways, but you're falling down, as seen down on the page. So you're going to end up somewhere over here. And because you had acceleration, right, your velocity vector has gone from going here. I've added a little bit of this velocity. So now we're going this way. But when I'm here, now my gravitational attraction, again, it's towards the center of the planet. So it's there. So that means that a bit later, this thing has moved in this direction, but also fallen towards the center. So it's going to end up more somewhere like here, maybe. And then the same thing keeps happening. Its acceleration is always towards the center, its velocity is always perpendicular, and because the acceleration is perpendicular to the velocity, right, so a 90-degree angle between those two, the speed of the object never changes. Now all of that is just basic uniform circular motion, so hopefully it was just a review. The fact that gravity is responsible for the turning here is sort of secondary. Right, but you can see what happens. You're going to follow this path that just takes you round the planet. Another way to visualize orbits that can be helpful if you're sort of struggling to figure out how, but why don't I fall down on the planet? Like, why don't I just eventually crash down? Here's a little picture that might help you. So imagine this is the ground. Right? Just flat ground, and there's a little tree here, and there's a little house right here, little chimney. Right, that's the ground, and here you are flying, right? So here you are. This is you know, Superman, or Superwoman, or super something else. There you are flying, and of course, you can't actually fly. You don't have superpowers, I assume. So if you somehow end up in this position here, going sideways, right, you're actually going to end up doing this. Projectile motion. And the faster you're going when you're up here, the further you're going to get. But eventually you're going to crash down here, and hopefully you'll survive that. Well, the Earth is round. Right? If the Earth was an infinitely flat sheet, no matter how fast you're going, eventually you would crash down. Well, the Earth isn't an infinitely flat sheet. It is spherical, right? So let's zoom in. Let's imagine I zoom into this bit here. So I might draw it like this. Right? It's a little bit of a curve I've drawn here, and here's my little tree, and here's my little house. There's a chimney. Right. Now you are flying here. There you are with your cape, right? Somehow you ended up there. You're going this way. Okay, you're going to fall. You want to fall down. But now if you go fast enough, you're going sideways and you're starting to fall. But as you're falling, the Earth bends away beneath you, right? If the Earth was straight, you'd be crashing here. But you don't, because the Earth is bending away beneath you. It's a very hand-wavy way to understand orbits, but it gets the right idea across. Right? But you have to go fast enough. If you're too slow, you're going to do this. If you're going too fast, you're going to, leave the Earth. But if you have the right speed, you're just your trajectory just bends down at the same rate that the Earth is bending down beneath you, and then it always looks the same, because I can just sort of rotate the picture. You always kind of the same position, because ultimately this is part of a circle. Hopefully that helped. So let's look at the math. So imagine I've got a planet here, and I want to say my planet has mass m, capital M. Here's my satellite, mass lowercase m. Now, satellite, again, could mean a man-made satellite, for communications, or it could just be a natural satellite, such as a moon, a tiny rock, right, that flies around the Earth. So, as we said, that if this was just sitting there, it would start falling towards the Earth, crash down, and if it's big enough, destroy all life on the planet. But instead, let's suppose this has a sideways velocity like this. If V is too big, the gravitational attraction of the planet is not going to do very much. It's just going to fly off, bend a little bit, but it's never seen again. If it's too slow, it's going to go, it's going to fall down, it's going to bend around, and you're going to bump on the Earth somewhere here. But what has to be true if we want this thing to be part of a circular orbit? It's not quite drawn right, but you get the idea. Circular orbit. Well, the force of gravity has to be just right to act as a centripetal force, right? So the force of gravity acts as the centripetal force. Now remember, the centripetal force is not a new type of interaction. It's a role a force or a combination of forces plays. Like the net force is a centripetal force if the net force is responsible for making the thing go in a circle, or at least making the thing go around a turn. And in this case, the force is just gravity. There's no tether of any kind, right? This is not some kind of example. You've got a giant cable. You can think about it. Maybe a space elevator might have that. We can talk about that another time. No, here none of that. It's just gravity that's doing the pulling, right? So what do we have? Well, we have the m over r squared, right? It's the force of gravity. So by r distance, r is of course this here from the center of the planet to where the satellite is. The force of gravity, that is the centripetal force. Well, the thing that's going around in a circle is not the planet, it's the satellite. So it's its mass, little m, v squared over r. Right? In a way, that is all we're ever going to need to calculate circular orbits. Now, of course, the masses here cancel out rather nicely. So, to make a note of that, note m cancels out, and m is the mass of the satellite. So, what does it mean physically? The fact is, cancels out the mass of the orbiting object is irrelevant. At least irrelevant in the sense of we don't care about it when it comes to calculating any characteristics of the orbit. How fast is the object moving? What relative to the size of the orbit? How long does it take to go around? All that stuff we can calculate without knowing the mass of the object that's going in a circle. Now, of course, we've met this thing before, especially if we plug in v equals 2 pi r over the period. Right, if we plug this in, we get back to Kepler's law, the third one of Kepler's laws that said that relates the period squared to the radius cubed. Now, the rest of the lectures, we're just looking at some examples of this. The first example I will look at is Phobos, which is the inner moon of Mars. Mars has two moons, Phobos and Deimos, and Phobos is right here. They're both tiny. Phobos has a diameter of 11 kilometers. So that's essentially like a mountain, a spherical or sort of potato-shaped mountain in space. So it's much smaller than Earth's moon, for example. It has a mass of a little bit over 10 to the 16 kilograms, which sounds like a lot, but again, it's a lot less than, say, the mass of Mars or the mass of Earth or the mass of Earth's moon. And as we just discussed, we won't actually need this value at all because the orbital characteristic of Phobos does not depend on its mass, right? You could put another object here, a little spaceship, let this orbit, and it would follow the same orbit even though it has a very different mass, right? Because the masses cancel like we just discovered. Its orbital radius is a little bit over 9,000 kilometers. Now, the radius of Mars is 3,400 kilometers. So I didn't quite draw it right. I think I drew it a little bit too far out. But it's almost 3 times the radius of Mars. Right, so it's like Mars again, Mars a third time almost. I drew it a bit too far out here. But it's roughly to scale. Alright, so we are asked to find how long Phobos takes to go around Mars once. Well, let's solve that. We do exactly the thing that we just talked about. I'm going to say that G times the mass of Mars times the mass of Phobos divided by the radius squared, right? That is the force of gravity that acts as a centripetal force. So I'm setting it equal to the mass of the object that's circling, that's Phobos, times v squared over r. I can cancel these ones. I guess I can cancel this with this. And, well, I don't want the speed. If I want to calculate the speed, I could just plug in values right now. Well, I want the period, so I'm going to use that the speed is the distance traveled all the way around divided by the time taken. That is exactly the period. So we're going to get G times the mass of Mars divided by r is equal to 2 pi r over t squared, because all the other stuff is cancelled out. And now we can solve for t. I trust that you can just rearrange this. Don't forget to square everything. The 2 becomes a 4, the pi becomes a pi squared, the r becomes an r squared. There's another r there, there's a t squared there. You rearrange it, plug in the values. What you should find is about 7 hours and 40 minutes. And again, I encourage you, post the video, work through it, just to make sure you can actually do it. Right, and you don't trip up somewhere. Maybe with the powers of 10, maybe with squaring the pi, all mistakes I've seen made in exams, for example. So make sure you at least practice actually punching in the numbers once or twice. But that's my answer, right? It's just doing exactly what we were just talking about. Second example I'm going to talk about are geostationary satellites. What does that mean? So satellite in this case refers to a man-made thing that gets shot up into space. For example, it's a communication satellite. Geostationary, geo, Earth, stationary, well, stationary. So what it means is a satellite that is above the same point on the Earth the whole time. How can this be? Don't orbits have to, like, go round and round, otherwise they fall down? Yes, but remember the Earth is of course spinning, right? So the Earth is spinning, and so if you position a satellite just right, it might make an orbit around the Earth, but always stay right above the same point on the Earth. So if you stand at that point on Earth, you can look up and the satellite's always going to be in the same spot, if you can see it, maybe with a telescope. So where might you find them? That's the question here. Well, let's have a look. So can we find them somewhere, say in the northern hemisphere? Right, so maybe if you're in North America, which many of you are, maybe you're right here. Then I can think, well, let's go up in the sky, and there's a little satellite right here. Maybe let's give it some solar panels. Right, there we go, here's my little satellite. Can this satellite stay above me the whole time? Let's think about this one. Where am I going to go? I'm going to follow a path like this. Alright? And then round the back of the Earth like this. This is behind the Earth, right? So we can't see it. So a little dashed line here. This is the path. Okay. Well, that means the orbit of this satellite would have to be essentially a sort of halo like this, right? Hard for me to draw. I can tempt it. It has to sort of go over here and then come round like this. As we go in here and here. This would have to be the orbit for the satellite, right? To always be above the same point on the Earth, somewhere in the northern hemisphere. Look straight up, this direction. So now you're over here, this direction, this direction. This is the path the satellite has to follow. Of course, that can't happen. Why not? Because that would require a force that's towards the center of the circle. The center of the circle is here. Well, that's not where the Earth is. The Earth is down there. Right? So impossible. What would actually happen is if you had a satellite there, right, and if it were not to crash, you get on a trajectory, it has to circle the center of the Earth down here, right? Because the center of the Earth is where the gravitational pull points towards. So the satellite really would be doing something like this. Now you can get it to do this over the course of exactly 1 day, so when you've gone all the way around, you'll meet it again there. But during the day, it's going this way, whereas you're going this way, so it's not above you. So that is impossible. So where can we have geostationary satellites? Well, if the circle that a satellite follows, the orbital satellite, has to be around the center of the Earth, then we have to be in a spot that circles the center of the Earth, right? Now, any spot on the Earth circles the Earth's axis, but to circle the exact center, you have to be on the equator. So we have to be on the equator, or in the case of satellite, above the equator. So we are on the equator looking up, the satellite is above us, always the same spot. Now, how high up does it have to be? Can it be any height? No. If it's the wrong height, say if it's really low, it would have to go very fast, otherwise it would crash down. Right? The speed of the satellite has to be a certain value given the radius, otherwise it would crash or fly off into the distance. You have to hit the right speed to have a circular orbit. So let's figure this one out. What do we have? Well, we know the period. The period of our satellite is 1 day, because that's how long it takes of me standing here to go around. Right, so 1 day, that's 86,400 seconds. Not a good little number to have up your fingertips. At your fingertips. Up your sleeve. Wherever you keep those numbers. Then we're going to need the mass of the Earth, and again that is something that we know by now. We've used it before. It's about 6 times 10 to the 24 kilograms. And so we're trying to find the radius. Well, let's, work through the same steps that we worked through before. We set the force of gravity. This is the mass of the Earth. I'm going to abbreviate with an E. This is the mass of my satellite, right, little m, is equal to m, the thing it's circling, v squared over r. Well, okay, the mass of the satellite doesn't matter, so your geostationary satellite, you're going to put them in the same spot no matter what the mass is, right? And we're going to use, once again, the v is 2 pi t over r, except in this case, we know t. So you can also cancel out this. So it's almost an identical calculation to before. Get 4 pi squared t squared. Oops, you probably caught this. 2 pi r over t, excuse me. We've cancelled out r squared. So this r cancelled with this one, but now we're going to r squared on the top divided by t squared, right? So we know g, we know the mass of the Earth, we know the period, that was 1 day. So you solve it, and we're going to find that the radius, excuse me, is something like 42,200 kilometers. Of course, the answer is going to be in meters, right? So 42,200 kilometers, but the Earth is 6,400 kilometers in radius. So let's draw this in a picture. If this is the Earth, right, and so this distance here is 6,400 kilometers, well, from the center, we are 42,000 kilometers. And again, make sure you get that value or something, you know, around there. This is, of course, you approximate values again. This isn't approximate, but this is approximated. So make sure you get that one right. But you get this value, 42,000, so that's, you know, rough 6.5 times this. So it's sort of somewhere out here. This is where I have to put my satellite. Here are the solar panels. Right, it's going to go in a big circle like this around the Earth. So they're actually really far out. And they have to be above the equator. So I shouldn't be drawing it like this. I'll be drawing it sort of like, you know, going in a big circle that's always above the equator. So it's perhaps surprising that they're that far out, right? But anywhere closer, you put a satellite here, it's got to go faster. The International Space Station, for example, is a couple of 100 kilometers above the surface of the Earth, and it takes about an hour and a half to go around, not 24 hours. Now what it means, though, is that on this circle, if you want to have a satellite that stays in the same spot, you have to put it on this circle. And there are lots of satellites for which you want to do that, mostly communication satellites. So there's sort of this crowded area in space, in this ring around the Earth, with this this radius of approximately 42,000-ish, well, 42,200 kilometers. Interesting fact, but ultimately the calculation was exactly the same as in the first example, right? So orbits, circular orbits are very, very simple. It's always the same. Force of gravity equals centripetal force. Force of gravity is the centripetal force. Okay, maybe I need to relate the speed to the period, depending what quantities I know, and solve for whatever it is that you don't know that you want to find. It's very, very mechanical to solve these orbit problems. Alright, thank you for watching, and I'll see you in the next video.